So what we're going to talk about right now is encoding and decoding of data, and what this is all about. Silly thing. So today is the 30th. So two things. Yeah, one is explaining what encoding and decoding is, and the other is how do we do it practically. So encoding and decoding is no more than the theory of how do we write things down and how do we understand them after we've read them. So encoding is how do we write things down, and decoding is how do we understand what we've written. Pretty dumb, huh? So the I mean, encoding, so how do we encode the number, any number? Let's just choose a number at random. Let's say 42. So the first thing to think is that the number 42 can be written many, many different ways. So in Roman numerals, we can write it as XLII, I believe, is 42. In Chinese characters, it will be what my Mandarin thing, so I can really show off here. Windows space, there we go, Mandarin. Yep. So that's 42. This is, of course, 42. If we were to write 42 in octal, it would be, well, how do we write 42 in octal? Well, 40 is 5 times 8, so it would be 52 in octal. And in base 42, what would it be? It would be 10. I'm doing this, I'm being sort of sarcastic. But, so these are all, hypothetical ways of encoding one number. What's the real 42? Well, the real 42 is the number that is one more than 41. If you go back to mathematics, there's a whole part of philosophy of mathematics and foundations of mathematics where they can define numbers in terms of set theory. And so there's something in set theory that can be represented as 42 or as XLII or CISH-R or 42 decimal or 52 octal or 10 base 42, or what have you. If you make one can imagine a hypothetical base 43 where the character for 42 was smiley face, right? So So we get to choose. So an encoding is how we choose to represent a number. So let's think about an encoding for 42. Let's talk about how we represent the letter A. How do we represent the letter A? In fact, there's like this whole standards committee called Unicode, which is all about these kinds of things, and it's just as weird as the mathematicians. In ASCII or Unicode, this is hex 62. Now, I've just represented a number, 62. So I forgot to put something up here, 42 in hexadecimal. That would be 3A. I'm sorry, 2A. 2 times 16 is 32 plus 10. Yep. So, but when I say hex 62, I don't mean the character 0x62, which is what I had to type. I mean that number, right? So we have a mapping. We've got all of these things in encoding, which are like that thing from Alice in Wonderland, where the name of the song is called I've forgotten what they were called. The song is Haddock's Eyes. That's the part I remember. I don't know if you've read Alice in Wonderland, but there's a long thing where the White Knight and Alice go through this thing about the song. So the name of the song is called blah. The name of the song is something else. The song is Haddock's Eyes and so forth. So, and a lot of this is about that kind of thing. It's like, how are we going to represent this in a different way? So if you were to look in binary, which is how computers work, and you look at the letter A, and I'm going to come back to the whole thing of like measurements here, not very long, it would be written out as 0, 0, 0, 1, 1, 0, 0, 0, 1, 0. Right. So but again, this is 8 characters. I just typed 8 characters. That's an encoding of that number, which is an encoding of that number, which is an encoding of the letter A. Why didn't I just type the letter A? Well, because we're talking about encoding now, and we're talking about how we represent things. Is this sort of, I mean, I'm certainly talking about stuff. I don't know if this is making sense, but now I'm going to make this more practical. Suppose we want to send data, and in particular, suppose we want to send the number 42. How do we do it? So, well, one way of doing it would be to send the 2 characters 4 and 2. So for example, if I wanted to send 42 as a measurement A and 5 as the measurement B, for example, right? You understand this? If you see 4, 2, 5, if you just see the characters 4, 2, and 5, you don't really know what it means unless you've established a convention. Often we might send a comma in between them to separate them. For instance, tell the receiver that it's really just 4 and 2, and there's nothing else coming. Now, sometimes the receiver can just receive 2 characters and just know that it's always 2 characters, but that's not always convenient. So in any case, we've got to set up a convention so that the sender and the receiver can agree that when the sender sends 42, that the receiver sees the 42 and knows that that's really the number 42. Now, if the receiver sees the characters 42, 4 and 2, how does it turn it into the number 42? Oh, my Chinese is still turned on. Into the number 42. Well, 4 times 10, 42 equals 4 times 10 plus 2. So we are close, but underlined, but four and 2 in the above are numbers. And 4 and 2 are characters. In fact, they are the computer represents those as numbers that are equivalent to hex 34 and hex 32. Yes, I do happen to have these numbers memorized in my head. You end up doing this if you've been programming long enough. So the correct formula is 42 is equal to 0x34 minus 0x30 times 10 plus 0x32 minus 0x30. So with a formula like this is often turned into, this is often hidden in a macro that turns a character into the equivalent digit. A macro that might be called something like 2-digit. And so and if you study this carefully, What would we have to do if a third character came along? Well, it turns out that there's a nice recurrence relationship, if you remember your mathematics. So you can just do another multiplication, minus 0x30 times 10 plus C2 minus 0x30. And then with this closes that parentheses times 10 plus C3. This is C2, sorry, typo. And so forth. So you can just keep adding. If you just take this previous quantity and multiply it by 10, and add the next digit. You can add as many digits as you like up to where you start to overflow the range of your variables, of your registers. So this is, so I could write a nice mathematical equation for this, but I think you get the idea, right? You can do this in a loop and just keep doing that. So that's how you would decode this. So how would we encode this? Suppose we've got the number 42 and we want to send it in this way. Well, we have to say, okay, I've got this number X. Now it's a little bit awkward because you'll notice, we're sending in this particular scheme, we're always adding least significant numbers onto the back, and we add and if you reverse the process, that means you're going to get the rightmost digit first. So you'd get C3. So since we're going to have to get these in the reverse order, I'm going to write this as an array. So C of 3 equals X modulo 10. Remember, the percent sign is the modulus operator. And then we're going to add X30. So now and then we can just continue this, X / equals 10. So we divide X by 10, and then we can say C of 2 equals X modulo 10 plus X30, and so forth. So, So, and then, so now we've got C, we set C of 0 equals X modulo 10 plus 30. And then we can then send so for example, this would send leading zeros. So if I put 42 into this number, what we get back is 0042. So you can get more, in a real world, if you're formatting decimal numbers, you get all kinds of crazy stuff to deal with the fact that we normally suppress leading zeros and all this stuff. But that's not where I'm going with this. I'm just trying to give you the notion that encoding and decoding is this step-by-step process where you're changing numbers into numbers. That's the key thing, because the computer still views C3, 0, 1 as numbers. And I mean, I've done arithmetic operation, but I say, but here I change my point of view. The whole thing about encoding and decoding is changing your point of view. On the one hand, it's a dessert topping. On the other hand, it's a floor cleaner. This is a joke from Saturday Night Live when I was a child. So you know, and this is one of the most powerful tricks in computer programming, is you learn to say, okay, this number originally came in as a number because it meant something, but I control how it gets interpreted in the way I write my code. So I can just say, oh, I used to view it as this number, but now I'm going to view it as a character. And you transmit it, and because of all that, once you put it into the stream of characters, it's going to show up as a character at the other end, typically. Not always, because you can have demented things that give you hex dumps or all kinds of strange things. But the main thing is that we keep going back and forth between the number in one form and the number in another form. Essentially, we're just doing busy work. We're not changing anything. We're just re-expressing. And if you've ever heard of Gödel's theorem, the whole Gödel's theorem, which is one of the most fundamental statements of philosophy in the 20th century.
Sorry, Terry, can you write it? Because
Yeah,
I don't know, I couldn't hear you.
G with an umlaut, G control shift colon O, yeah. Control colon O, yeah. Control shift O, so what Gödel, it's German, so that's actually, I said, I can't get this guy to do an umlaut. We'll just write it this way. You can look it up. What's important is the way he proved it was by doing exactly this kind of trick in mathematics, slightly before computers were invented. He said, geez, we can write a formula. We can take every formula of mathematical proof and look at each letter and assign a number to each letter. And we can make a formula so that we have, this formula x equals y plus 3 is equivalent to the number 3,055,055. Okay, and so every formula could be translated into a number. Well, that's exactly what we're doing here. Everything inside the computer can be translated into a number. When you're writing in C, what you're really producing is a string of numbers that the computer turns into a different string of numbers, which is the instructions for the computer. So it's really, really useful to learn encoding and decoding, even though it's really kind of mind-breaking and tedious at first, because it teaches you that things really depend on how you look at them. Not, they don't have, in human discussions, we tend to feel that things mean what they say they mean. What we say they mean, that right is right and wrong is wrong and all this stuff. But in computers, it's all depends on how you look at it. And if you can learn to do this, then and do this intuitively, then it's really, really helpful. So now I've talked about encoding in the abstract. Now let's talk about encoding your numbers for LoRa. We want to be terse. So So we choose encodings that don't send many more bits than we need. How do I mean? Well, 42 is approximately 2 to the 6th. Which means it takes about 6 bits to send 42. But now, if we send it as 4 followed by 2 is 2 bytes, 2 characters, which is how many bits? How many bits in a byte? That's a question.
8.
Right. So that's how many bits in 42 written this way?
42.
Or
I don't know.
if I write 4 followed by 2 to represent the number 42, how many bits have I taken?
16.
Right. So this means that we have, this means that we are about 40, less than 40% as theoretically possible. So, in fact, maybe even better, 6/16. So, however, so if we're representing a number in the range 0 to say 1,000, that's only 10 bits of data, because 1024 is 2 to the 10th. But if we send 3 characters, that's 24 bits. Same kind of inefficiency. So so that means that we're spending, every time we send a message, we're wasting 2/3 of the message, roughly. So so an easy way to, so there are lots of ways to be more efficient, but one way is to just make sure that we send only a small number of bytes. So encoding is always there's a tension between the maximum efficiency and coding simplicity. A trade-off between if we only send 10 bits, which is in the case of a number in the range 0 to 1,000, then that's really very efficient. But if you have 2 numbers, packing 2 10-bit numbers into a 24-bit number or 3 into a 30-bit number, it gets really, you get all of these boundary conditions, and it gets kind of tricky and gets hard to read when you're looking at the received data. So so it's very common early in projects to use byte boundaries as a compromise, which means you send 8 bits or 16-bit or 24-bit. And the other thing you do is you look at you look at the accuracy of your measurement. If you've got a social security number, you've got to send, or your passport number or something like that, you've got to send the whole thing. But if what you've got is a measurement of temperature and you only have 1% accurate sensors, it may not make sense to send more than 8 bits. So don't waste battery encoding noise. I mean, sometimes your sensor may be 1% accurate, but actually there's interesting data, that down in the lower digits, you might have something where you even 10th% would be interesting because it's repeatable and stable. It's just not the right answer. It's just off by somewhat. You might be able to calibrate it out later. You might be able to use the relative differences for some purpose. So you might want to send that. So you have to use your human judgment to look at this stuff and say, well, there's, I've got these extra bits, I want to send them. So if you've got an A to D converter, that's a 12-bit A to D converter. So it might make sense to send all 12 bits, but it certainly doesn't make sense to send 24 bits of data for a 12-bit measurement. And you can use your judgment by looking at the specifications on your sensors and this kind of stuff. If your sensor is sending you 32-bit numbers, because that's what it does. I mean, I've got some Sensorion sensors that send you 32-bit floating point. Well, for sure, they're not measuring anything like that accuracy. And so you can sort of work backwards. So, so there's 2 cases and then I'm going to have to finish up. So encoding. So the first case is where a simple range where your sensor is like a humidity sensor, where it just goes from 0% to 100%, or a temperature sensor that goes from, say, -20 C to 80 C or something like that. So by not very wide, I mean, your range of values is like 0 to 4096 or 0 to 65535. Those are powers of 2. Yeah. So you can map the value onto 2 bytes. Each byte represents a base 256 digit. A little bit hard to deal with, a little bit hard to think about, but each byte is a number between 0 and 255, right? I say this so quickly because, again, I've been doing this stuff for 50 years. And so I just know that the maximum for a byte is 256 and 2 to the 8th is 256. And so 0 to 255. So you can do number systems in any base. I mean, when I was growing up, they taught us base 8 and base 10 at the same time, and new math, it was called. So you can say B1 times, remember my formula, my previous formula was here. Remember C times, this was base 10, so that's why this was 10. And this C1 was getting this guy into a range that I could multiply it by 10. But guess what? with base 256, there's no waste, there's no offset, there's no encoding. Base 256 is like every single value has got a significance. So we can just say, so for example, we have X is equal to, this is, we're again, we're working from decoding C1 times 256 plus C2. C1 and C0 and C1 are the 2 bytes. And now it's traditional. In this particular case, we just have fixed length fields. There's still the question, which one do you write down first? So remember, I mean, you must have encountered big endian versus little endian. This is just big endian versus little endian. C1 followed by C0 is little endian. C0 followed by because in this particular case, this is the bigger, this is the bigger value, right? Because it's times 256. So big is first, and little endian is the littlest first. So so to encode, if this is how we're going to decode, C0 equals X divided by 256. C1 equals X modulo 256. Now, if you're familiar with binary arithmetic, I'm going to have to leave like really soon. If you're familiar with binary arithmetic, you will immediately know that these two operations, dividing by a power of 2 and modulo a power of 2, can be done very efficiently using ands and ors. So it turns out that that X slash 256 is identical to X shift right 8. And shifts are much easier than divides. And X modulo 256 is identical to X and 0xF. Why? Because X modulo 256 is just the bottom 8 bits of X. And so, and what does this mask do? It has ones in the bottom 8 bits. If you count, F is all ones. So there's 4 ones and then 4 ones concatenated. So that's 8 ones in a row. So X and those 8 ones throws away the high order bits and gives you the low order bits. So you will often see these kinds of things in code because embedded programmers know this, particularly embedded programmers who've ever had to do assembly language, and they've reached for the document of their microprocessor for the divide instruction, and they discover there's no divide instruction. You have to call a subroutine. It's slow. There's no modulo. It's slow. But powers of 2, shifts and ands are always relatively cheap. So there you go. I'm going to have to stop. I was going to talk about encoding longer ranges, but sometimes your sensor doesn't value over ranges of, sometimes your sensor value varies over wide ranges of values. A light sensor, for example, can range over several orders of magnitude. So it can, what you do then is you use a representation where you use the logarithm. It's called floating point. And if you think about that and then go back and look at what I wrote for my various encoders for floating point, that's what I'm doing there. And we can talk about that again next week. but I better go now. Thank you all. I'll post this stuff.
Thank you too.
I hope this helped. If not, if not, you can tell me later. Bye.
Bye.
Bye.